Okay. Yeah, discussing about possible routes to decarbonize steel and iron industries and the role of hydrogen. In this talk, I will start with some basic overview of steel and iron manufacturing, followed by facts and figure in steel manufacturing, the role of steel in net zero emission. The key point I will be discussing is the possible routes to decarbonize steel and iron industries. While discussing possible routes, I will also talk about challenges include. Before concluding, I will discuss about techno-economics and technology readiness level of those technologies. Finally, I will conclude with some recommendations. Here is the key figure in steel and iron manufacturing. About 1900 million ton of steel is produced worldwide, and China is leading the industry with 57% of the world. India, Japan, USA, and Russian Federation also are producing about 5% each. Europe is producing, Europe and other Asian countries producing about 25% of the steel. Just to mention, Australia is producing a very low amount of steel, ranking 29th in the world. While talking about the steel production technologies, as you can see in the right-hand side, this technology is leading by blast furnace technology, which produces 73% of the steel, and the rest, about 26%, is produced from electric arc furnace. Here is the world emission and energy scenario. As we can see in the left-hand side, about 550 exajoule of energy is produced in 2020. Out of that, 68.5 million exajoule was produced from renewable sources. However, the gap is decreasing over the is projected to be decreasing in 2050. About 30% of world energy will be produced from renewable sources. In the right-hand side, as you can see, the total CO2 emission in 2022, about 34 gigaton of CO2 was emitted. Out of that, 25% was emitted from industries. Out of that 25%, which is equivalent to 8.3 gigaton, out of this 8.3 gigaton, steel industries produced one third of this emission, which is equivalent to 7 to 9% of global CO2 emission, which is 2.75 gigaton. And this industry is very energy intensive industry. It requires about 8% of the energy we generate worldwide. Okay, so the main ingredient of iron and steel manufacturing is the iron ore. As you can see from here, that iron ore comes from our mines in the form of either hematite, magnetite, limonite, siderite, and pyrite. And this category is based on the iron content in the ore. In the bottom figure, as you can see, so the appearance of a different iron ore we produced in Australia, especially in Western Australia. As you can see, the composition about 55 to 67% is iron, and the rest is aluminum oxide and silicon dioxide. And the quality of the iron also depends on the impurities or gangue contents in our iron ore. As you can see in the figure, different countries have different qualities of iron ore. In Australia, around about 62% is iron. In order to directly shift, this content has to be about 62%, and that has the quality in Australia, India, Brazil, and Africa. Okay, so here I have mentioned the Australian iron reserve and the production capacities. As you can see in the left-hand side, Australia is the largest exporter as well as the largest reservoir. About 36% of iron is exported by Australia in the world. We have 28% of the reserve in the world. Some other major countries which has like largest reserve include Brazil, China, India, Russia, Canada, and so on. In the right hand side, you can see the Australian industry in terms of exporting iron ore is booming over the years, starting from 1962. However, the major breakthrough we can see since 2000, while China started producing iron and steel in a large scale, and China is the main buyer of our iron ore. About 900 million ton is produced in Australia, and about 836 million ton is exported around the world. In the right hand side, as you can see in the figure, our export revenue is around about 350 billion. Out of that, 150 billion is coming from iron ore industries, of course, which is 44%. However, our steel manufacturing is quite low, and we can only meet our local demand, which is 5.5 million ton. While discussing what are the technologies that uses to produce this steel, as we can see in the world figure, 74% from a blast furnace, basic oxygen furnace route, and the rest 26% from electric arc furnace. Our export industry is zero at the moment. However, one study shows that if we can grab 1% of the international market, then we can generate 6.5 billion in revenue with an addition of 4,000 jobs, which is a huge industry, but that industry has to develop here. Okay, let's talk about conventional iron and steel manufacturing technologies. So I have mentioned the two. One is iron making, another is steel making. How you produce iron? Iron is produced from iron ore, which I have mentioned here in the right hand side. As you can see, it is hematite, Fe2O3, and that has to be reduced in the using different reductant, which predominantly CO, carbon monoxide, as well as hydrogen. Okay, so what happens if we use CO that end up with iron as well as CO2 as a byproduct? On the other hand, if we use hydrogen, then in addition to this iron, we produce water as a byproduct. Okay, so so the leading technology is blast furnace, of course. In this technology, 73% of steel is manufactured. Lump ore, sinter, and coke is introduced in the blast furnace. And from the bottom, we introduce pulverized coal and hot blast to melt it. After melting after removal of the slag, that goes to basic oxygen furnace for the steel making. The second, the dominant route is directly using scrap in the electric arc furnace, which produces 21% of our steel. The third major route is use of direct reduced iron. So the difference here between the blast furnace route and this route is to, instead of melting iron ore, we reduce in the solid form. This is solid state reduction, and then introduced into the electric arc furnace. For this reduction, we use either shaft furnace or a series of fluidized bed reactor. The fourth category I have mentioned here produces very little amount of steel, less than 1%. But this is one of the important and important technology to mitigate CO2, because in this system we eliminate the sintering plant. Instead of using sintering plant, we directly introduce our ore and in the smelter and fine coal. And that after melting, that goes to oxygen furnace for the production of steel. Okay, so this is the basic overview of our current steel manufacturing. In the next here, I have mentioned the specific CO2 emission from a different steel manufacturing. As you can see, blast furnace technology actually produce about 2 tons of CO2 per ton of steel manufacturing. But depending on the sources, for example, natural gas or DRI, that emission reduces 15-20%. The second major route is, as you can see, electric arc furnace. Again, depending on the consideration or the resources we use, either renewable energy or grid electricity or natural gas or hydrogen, this emission varies. The third one is hybrid, which is under development in Sweden using hydrogen-based technology. However, one thing has to be mentioned here is that this is not absolute value. Rather, it vary. There is a large error bar here. In different studies shows considering different aspect, this blast furnace route can produce starting from 1.8 to 2.5 ton of CO2 per ton of steel manufacturing. Okay, so there are a lot of assumptions and considerations here. Okay, so what is the role of steel in to achieve net zero emission? According to Paris Agreement, in 2015, we produced 2.8 million tons of CO2. However, in order to reach a Paris Agreement, achieve Paris Agreement, that has to come down to 400 to 600 million ton in 2050. However, our steel industry is developing, growing from 2015 to 2050. A significant growth, about 900 million ton, will be increasing between this 2015 to 2050. So the key target here would be reducing CO2 from this existing steel making process. And in order to reach this Paris Agreement, we need to reduce at least 90% of our current level, which will be equivalent to about 200 kilogram of CO2 per ton of steel manufacturing. Okay, so this is a typical process flow diagram of blast furnace steel making. So this is the strategy I have. This is the number one strategy I have mentioned here, is utilizing hydrogen and biomass or biochar instead of using coal coke and natural gas. As you can see, I have mentioned some of the points where we use coal coke and coal coke based coke oven gas. This is the coke oven gas going to the blast furnace. However, if we can replace these sources with the renewable biomass as well as hydrogen in this point, then a substantial reduction is possible. Primary trial shows that about 20 to 50% reduction is possible. However, there are challenges in terms of biomass. How we're going to source our biomass sustainably? This is one of the issue. Biomass contains low energy content compared to coal coke, and this has a low physical strength compared to compared to char, compared to coal coke. And of course, the cost of biomass is several times higher than coal. Especially if I talk about Australia, it's at least 3 times higher than coal coke. What are the problems while using hydrogen in this blast furnace route? So the key issue here is maintaining the temperature. As I have mentioned here, the equations, if we use CO or natural gas, which of course come down to CO after reforming, then it is an exothermic reaction. That means we don't need to supply heat from external sources. However, if we use hydrogen, this is an endothermic reaction, meaning we have to inject or supply heat from the external sources. Therefore, the balancing heat or the temperature especially in the bottom part of our blast furnace is a challenging issue. Therefore, the use of hydrogen has to be limited. And that leads to the importance of using carbon capture technology. Okay, and the other issue is how we can supply the huge demand of hydrogen for this industry. So the good point is the CCS technology is developing. According to International Energy Agency, the CO2 capture by 2050 would be 1.6 billion ton. However, in order to develop this technology, we have to solve some of the key issues here in CCS technology, because this technology is currently not affordable or a bit expensive. Finding suitable source or geological structure is on another issue in this CCS technology, and of course contamination of water and leakage are some of the key problems in this CCS technology. Okay, the second strategies I have mentioned here is using electric arc furnace and scrap. So this right hand side shows typical resources we use for electric arc furnace. Electric arc furnace does not necessarily use electricity only. However, we give a lot of chemical energy from different sources, for example, tar and coke and natural gas. So if we can remove or reduce the use of those sources, which are fossil fuel waste, then there is a substantial substantial amount of CO2 can be reduced from this technology. And I have mentioned these are the possible routes or point where we can inject green hydrogen. One is electric arc furnace, another one is a reheat furnace. However, there are challenges. High quality steel scrap, high quality steel scrap is not available at this moment, and of course, still as we use. So the quality degrades due to the contamination of, for example, copper and nickel. So a challenging issue include renewable hydrogen sourcing, renewable electricity, biochar or charcoal. So there are a whole lot of challenges here as well, but as technology develops, probably we'll be able to come up with some solution in this regard. The third strategy here is using a DRI along with scrap in electric arc furnace. This DRI technology is also developing over the years. Starting, if I talk about since 2006, it has gone double over the between 2006 to 2020. Currently, over 100 million ton of DRI is produced using different technology. As while talking about technology, MIDREX is the leading technology. MIDREX and Hayeswile, they use actually shaft furnace and produce over 70% of the DRI in the world. Okay, so this is a typical process flow diagram from MIDREX for the manufacturing of DRI, as we can see in the left-hand side. However, this is actually the natural gas based, but recently they have started introducing hydrogen. As you can see at the top, this is the hydrogen injection point. So in this natural existing natural gas plant, they are introducing hydrogen, and they have mentioned that about 30% of hydrogen is possible without process. 30% injection of hydrogen, or I would say replacement of natural gas, is possible using renewable hydrogen without process modification. So they are in the transitioning phase at this moment. Predominantly they are natural gas based presently. However, they are in the transition. They will be starting from 20, 50, 70%, and of course CO2 will be reduced. CO2 emission will be reduced linearly as you increase the concentration of hydrogen in the system. And finally, they have the plan to use 100% hydrogen, which they have shown promise in their trials that it is possible to use 100% hydrogen in their shaft furnace. The fourth strategy here is hydrogen plasma smelting reduction process. This is a direct reduction of iron ore using hydrogen plasma. As you can see in the right hand side, renewable hydrogen produced from electrolysis, as well as the electricity goes to the smelting reductor, produce hydrogen plasma with very high temperature that melts iron ore and directly produce steel. So the benefit of using this technology, it has 95% potential to reduce CO2 compared to blast furnace technology, and this process has also a better potential to produce better quality steel compared to DRI based electric arc furnace. The challenges is this is very early stage of the development, and the technology readiness level is about 5 in terms of if I consider the scale is in 9. The fifth strategy here is alkaline iron electrolysis. This is electrowinning, a direct reduction of iron at low temperature. So in this technology, the one of the additional thing is we leach our iron before introducing in the electric arc furnace, and then producing making iron pellet. And with the addition of renewable electricity and oxygen, we produce steel. Um, so this technology actually has the potential to reduce CO2 emission 85 to 95% with 30% lower energy demand compared to blast furnace technology. And the reduction of efficiency in this technology depends on various factors, which include impurities of iron ore, current density, types of electrolysis, and their concentration. However, as I mentioned previously, with HPSR process, this technology is also early stage of its development. The technology readiness level is at 5. The last strategy I have mentioned here is molten oxide electrolysis. So in this technology, it is metallurgical techniques to produce steel directly from iron ore. As you can see in the right hand side, the fine iron ore goes to our electrolysis cell. Electricity and oxygen and some other additives is introduced here. Oxygen is removed before, and then steel is manufactured here according to this equation at the bottom here. Typically calcium oxide or magnesium oxide are used as a molten oxide, and electricity of course as a reductant. This technology has the potential to reduce CO2 about 100%. So this can essentially produce, has the capability to produce pure, good quality pure metal. This is very simple process, no hazardous waste. However, the challenges include this technology is very slow. This process is very slow, and it requires a lot of capital investment, like a huge number of cells, electrolysis cells. A low current efficiency, high heat loss, and availability of cheap and iron carbon-free anode is also challenging. But there are a lot of research going on in this area. At this stage, the technology readiness level is at 4. Okay, so what we have understood from this talk is what we need is affordable hydrogen, right, in order to decarbonize the industry. So let's talk about hydrogen a little bit in a couple of slides. As I have mentioned here in the left-hand side, about 90 million ton of hydrogen is produced worldwide at this moment. However, this is solely fossil fuel based, predominantly steam reforming. Okay, so that itself produced 900 million ton of CO2, which is equivalent to 2.5% in the world. So if we cannot produce enough electricity using renewable electricity, there is no point of using hydrogen in other processes. So this hydrogen is out of those 990 million ton we produce, 10% is used in DRI manufacturing, which is essentially goes to our steel manufacturing. But according to Energy Agency, International Energy Agency, 560 million ton will be produced by 2050. Okay, so some techno-economics of hydrogen energy. As we can see, fossil fuel waste carbon capture technology integrated with carbon capture in technology is already in developed phase, and it is affordable as well, because we can produce within our well-known $2 per kilo hydrogen price. Okay, but there is no point, as I mentioned, without carbon capture and storage technology using natural gas or coal gasification. Currently, renewable-based hydrogen price is very high, ranging from $3 to $8. But the promising figure is by 2050, it will come down significantly between $1 to $3. However, the key figure I should mention here is the electricity price. If we cannot produce electricity with lower price, then we won't be able to produce hydrogen with this $2 per kilogram. At this moment, our in Australia, our electricity price is near about $100 per megawatt. That has to come down to about 40 to 20 megawatt, $20 per megawatt in order to reach this target. But the good point is electricity generation from renewable sources is increasing from 30% around the world. At this stage, it will go down. It will go up to about 60% by 2050. And also Australia is also leading in this area in terms of producing electricity from renewable sources. Okay, so this is the modeling from CSIRO. They have predicted by 2025, in best case scenario, it is possible to produce hydrogen using renewable electrolyzer or electrolysis technology between $2 to $3. However, their assumption is the electricity price will come down to between 40 to $60 per megawatt. If we cannot reach this goal, it is impossible to produce with this price. Okay, so some snapshot of how much hydrogen we need in order to produce steel. We have calculated that 30 kilogram of hydrogen is required for reducing 1 ton of iron. 104 kilogram of hydrogen is required in order to replace the amount of energy we need compared to blast furnace technology. If we consider 1 million ton of steel per year capacity, that will require 12 ton of hydrogen per hour. So in order to generate this amount of hydrogen, we have to have 600 megawatt of electrolyzer with an efficiency of 70%. Okay, so in this slide, I have shown some of the existing technology which are well established, particularly in the top. So they are established and are operating in the commercial scale. However, the price actually, the capital cost varies significantly if we consider the latest or emerging technology. For example, molten oxide technology, the capital cost would be about 9 times higher than blast furnace technology. Alkaline iron electrolysis technology will be 7 times, for example. However, the good point is the operating cost would be somewhat similar to blast furnace technology, as you can see in the right hand side, or even lower than existing blast furnace technology. So these are some of the technological advancement around the world, and I have mentioned in 3 categories. So what are the potential of those technologies in terms of reaching net zero emission goal? As I have mentioned, the very high in potential, medium in potential, and high in potential. If I talk about high in potential, very high in potential, this hydrogen-based DRI or natural gas-based DRI has very high in potential in terms of achieving net zero emission target. And by 2030, we will be able to reach industrial development. The other one is medium in category, which include like introducing hydrogen, or substituting some amount of carbon from using biochar or biomass, or using smelting reduction technology, which currently produces very less amount, 1% of the steel around the world. The third category I have mentioned here is the emerging technologies, which are hydrogen plasma, AIE, and MOE. So these are in the development phase. So that will take a lot of time to reach industrial development. Some organization predicts it will come online in industrial phase even after 2040 or 2050. Okay, so the key takeaway from this talk is hydrogen-based blast furnace technology can be a short-term solution, or using affordable. If we can implement affordable CCS, that can be high in potential in terms of reducing CO2 emission. Carbon neutral biochar can be introduced in the blast furnace or in electric arc furnace to reduce CO2 emission. However, the most promising one, I should say, is hydrogen-based DRI and electric arc furnace in terms of technology readiness level and net zero emission potential. However, the main problem in this technology is, beside sourcing renewable hydrogen, is sourcing high quality iron ore. Because if we use a low quality, low grade iron ore, which is less than 66%, then there is a problem in the gangue content, like impurities. Then some companies around the world are suggesting to use intermediate melting reactor before putting to the blast oxygen furnace to remove gangue content from the DRI. And of course, we need to have affordable hydrogen in order to implement in this industry. Therefore, not only that, we have to have thorough investigation in the process as well, in order to check the quality of hydrogen-based steel manufacturing, and that may lead to our modification in our process. And then developing safety protocol is also important things in hydrogen-based industry, because this is not safe as a natural gas. We need to investigate our social impact in order to see the changes, so social impact of our shifting. And of course, who will take the leadership? Australia has the very good resources in terms of natural gas as well as the ore. So what we can understandably say that it can take the leading role in terms of developing this hydrogen-based technology, and together we can solve the problem. Thank you, and happy to take any question.